city. And that's kind of where I feel yesterday. All right, so I just want a quick recap here. Maybe you want to add this into your notes from yesterday. But here's just some rando function that I've drawn. Doesn't matter. It's just a nice little function. Where, oh where, does this graph have a relative maximum? Does this graph have a relative maximum? Ashley, where do you see a relative maximum? It's not a trick question.
Oh, wait. Is it the one on the left?
This guy over here?
Yeah.
Okay, I would agree that that is a relative max. That's not the only one. This one counts as a relative max as well, and some of you are like, but why? Why? Jose, why is it also a relative max? To be a relative max, our definition of relative max is that the function does something really special, and what is that special thing? The function changes from increasing to decreasing. I never said the derivative has to also be 0. The function has to change increasing to decreasing. The function is changing increasing to decreasing. Are we okay? Is there a relative min?
No. No.
There's no relative min?
Yes.
Right over here is where the graph changes from decreasing to increasing. Okay? Is there an absolute max?
Yes.
Yes.
Eric, you see an absolute max? Where do you see an absolute max? All the way up here. Wait, the place that's a relative max is also an absolute max?
Yes.
I completely agree. Eric convinced me. Why is that also an absolute max? Don't overthink it. Why is it the absolute max?
The highest point.
It's the highest point of the graph. Done. Where's the absolute min? Ashley, why is there no absolute min?
Because it's infinity on both sides.
Well, the graph decreases forever, so there is no absolute minimum, and all the friends are okay. Now, here's the thing. What if I change the graph and I said, only look here. Only look on this particular interval. All my relative maximums are still relative maximums. My relative min is still a relative min. My absolute max, still an absolute max. But now I get an absolute min. Where's the absolute min? Everybody knows it. Okay, Jose was pointing to it. There's the absolute min. Visually, I think we're good. I think we are 100% okay. If I gave you a graph and said, where's the absolute max, the absolute min, relative max, relative min, I would expect like 100% we get this under control. Yesterday, and here's where I blew it. I jumped too quickly. We started looking at problems then, like I took away the graph, and I just left you with the function. And the point that I needed to make, and I didn't make, I really didn't make this clearly enough, is that when we look for an absolute max or we look for an absolute min, there's only two places an absolute max or an absolute min could be. One of those places is the endpoints of the interval. The highest point either happens at the very end, like this guy does, or where's the other place that you might have an absolute extrema? If it's not at the endpoint, it's somewhere on the inside. But if it's somewhere on the inside, then it's a place like this. It's a place where it's a relative max. If you're on the inside, your absolute max could be your relative max. Kind of okay? I should have made that point clearer. That was so clear in my notes, and the words didn't come out of my mouth. So when we're looking at functions on a closed interval, your absolute extrema happen at endpoints, or where the derivative is equal to 0. Not derivative equal to 0. It happens where you have a relative max, relative min. This is where it looks. So here's what I want to do. Rather than going over the homework from last night, I want to give you guys some time to get started on the homework for tonight. We're going to do one problem together, just start to finish, so you've got good notes to follow. And then you guys are going to get a little bit of time to practice this, because we are going to go to a scary place right after this, which is absolute max and absolute min in application problems, which is so much fun. If you ask any of the BC students, any of the alum, the BC friends at Northside, the absolute toughest topic in the whole entire Calculus AB curriculum is what we're going to start in about 25 minutes. Oh my God, I'm so excited. And I'm all alone. Okay, that's fine. There are kids in Ohio that are loving this stuff. All right, so tonight's homework is on page, oh, so awkward. Okay, all the way in the back, all the way, where are you? Oh my God, awkwardness. It's absolutely a Friday.
67.
67. Kaylin, thank you for being there for me. I feel the love. Okay. Homework this weekend is to do all 4 of these. Right now, I'm going to do one of these from start to finish, so you've got another good model in your notes. Okay, Jose, you ready back there? Okay, you look like you're mentally preparing, nap time's over. Alright, so for all of these problems, the question is going to be, where's the absolute max, where's the absolute min? You do not get to use your calculator, not even a little bit. Not even a little bit. Okay. Find the global extrema. Global extrema is another way to say absolute max and min. We looked at that vocab yesterday. Okay, global is the same as absolute. Extrema is the same as saying max and min. The function is f of x equals 2x minus 3 times the cubed root of x squared on the interval 0 to 8. And I would expect absolutely no one in this room to know what this graph looks like. That's not the point. If you had the graph in front of you, absolute max and absolute min would be easy to find. You could point to be like, I get it, I get it, I get it. So, but what do we know? What do we know about where the absolute extrema live? It's either endpoints or it's inside the interval at like horizontal tangent lines and cusp points, which is why your first move, like I might identify the endpoints. Okay, my endpoints are x equals 0 and x equals 8. That's great. But I need what I keep calling those internal candidates, the ones inside the interval where I might have an absolute max and I might have an absolute min. So to get the candidates, this is where we need the derivative. We need to figure out where is the derivative equal to 0, or where does the derivative not exist. Well, let's find the derivative. F of x equals 2x minus 3 times the cubed root of x squared. This is the kind of derivative I would expect everybody to be able to do. Maybe you want to rewrite it first before you actually go and take the derivative. 2x minus 3 times cubed root of x squared. This is not something I have memorized, but there's some algebra that we can do to make life a little bit better. Okay. Well, this is the same as 2x minus 3 times x to the 2/3. Right? Cubed root of x squared is going to be x to the 2/3. All right, go find that derivative. The derivative of 2x is 2 minus the derivative of 3x to the 2/3 power. That 2/3 is going to come down and we're going to multiply. So we've got 2 plus x to the, what do we get?
Negative 1/3.
Negative 1/3. That's the derivative. The reason that we're finding the derivative, Jesus, is we're going after those candidates, those places inside the interval where I might have a relative max or a relative min. So what we need to do is we need to figure out, well, where is that derivative? Where is 2 minus 3x to the negative 1/3 equal to 0? Well, 2 minus 2x to the negative 1/3. And it stops being a calculus question and it starts being an algebra question. What can I do to solve this equation? 2 minus 2x to the negative 1/3. Maybe you want to subtract 2 to the other side. I might even like focus on this negative exponent and be like, God, that's really ugly and confusing for me. But a better way Right? It's the same thing as saying cube root of x, but in the denominator, is equal to 0. And now I heard folks say subtract 2 from both sides, that's great. I heard somebody else say multiply by like cube root of x, be that fraction killer that I was back in the day. Multiply everything through. Cube root of x times 2 is 2 cube root of x. Cube root of x times 2 over the cube root of x is 2. That should be a much easier equation for everybody in the room to solve. 2 times the cube root of x is equal to 2. That means that the cube root of x is equal to 1. And you know what x is. Or not. Cube root of x is equal to 1. So x is equal to 1. What's so special about x equals 1 is that your derivative is going to be equal to 0. We're expecting a horizontal tangent line, and that's what we look for a relative max or a relative min. And I would call this is a candidate. Is it a candidate that's inside the interval?
Yes.
Check the interval. Is it inside the interval? Absolutely. This is so some people even call it like an internal candidate. Now, there's one more thing to think about with this derivative. We figured out where the derivative is equal to 0. Could the derivative not exist? Could the derivative be undefined? Where does that happen? F prime of x is 2 minus 2 over the cube root of x. Is there a place, are there any values where the derivative doesn't exist?
0.
At 0. At x equals 0, f prime does not exist. Is that an internal candidate? Evelyn seems to think it's an internal candidate. Jose thinks it's an internal candidate. Abraham's nodding along like he does. It's an internal candidate for him. 3 people in a row are absolutely wrong.
No, it's open.
It's an endpoint. So is it an internal candidate?
No.
No. It's a place that we're going to check out anyway. You might argue that it's a candidate, but it's not inside the interval, so it's not internal. Okay, here's the good news, guys. We are about 30 seconds away from being done. We know that we're going to check the endpoints because that's a place where the absolute max and min happen. We're also going to check the internal candidate because that's the only other place it could happen. So it's just a matter of going off on the side now and doing the evaluate step. So we're going to evaluate the function at 0, we're going to evaluate the function at 1, we're going to evaluate the function at 8. Okay? When I say evaluate at 0, all I'm telling you to do is plug in and like keep writing because that'll keep you awake. Okay, 2 times 0 minus 3 times the cube root of 0 squared. A little ugly, but you guys are 100% okay with doing this? What is that?
0.
That's 0. F of 1, 2 times 1 minus 3 times the cube root of 1 squared. Right, 1 squared is 1, cube root of 1 is 1 times 3. Is that negative 1?
Yes.
Okay. F of 8, 2 times 8 minus 3 times the cube root of 8 squared. 8 squared is that 64?
Yeah.
Cube root of 64 is 4. 3 is
12.
12. 16 minus 12, we're going to get 4. We're about to make the conclusion. We identified the endpoints. The endpoints are usually easy because they're given to you. You find the derivative to figure out where I have those internal candidates. And now it's just a matter of looking at the data. Where's the absolute max?
8, 4.
Absolute max at 8, 4. I know that because this is the largest y value. Where's the absolute min?
1,
And the absolute min is at, where do we just say?
1,
1, comma negative 1. Is this making more sense than yesterday?
Yes.
Okay, my bad. I jumped way too quickly. We're not even going to look at the homework that you guys did last night. I'm sorry, Naum. Please forgive me. I failed you most of all. Can I what? Can I at least do number 4? I might be so swayed to do that. Here's what I'm going to do. I want to give you guys the next 10 minutes in your groups. Tonight's homework is to finish off 2, 3, and 4. You've got number 1 done as a perfect model. Understanding is so much better. You get the next 10 minutes. Show me what you can do. Beto, it's going to be okay. Okay? I'll leave this up here. 10 minutes for some good practice time. Oh, see, man, we've worn a hat for a little bit of the day. You have to wear it for the whole day now. You have cat head. Okay, 10 minutes. What's up, sir?
Will you explain this?
I'll show you my solution. Okay, homework pile over here. Homework pile over here. Hey, I'm an uncle. Yay! I had nothing to do with it. I was here. Emily Eliza DeRozier, 8 pounds, 20 ounces. What? No, 8 pounds, 2 ounces. Okay. Yeah, Eliza was my grandmother's name. Emily Eliza, nice job. Good job. Good job. Good job.
Okay, so when we finally do
See, hold on. It's 2 theorems. So 1.
wait, what?
Oh, you right.
Wait, no, you're the first one first, right?
Delia.
Minus 4.
Okay, Keith, you just told me that you turned on the corrections now, right? The test corrections?
They were all together. Well, it was.
I didn't see many corrections. Can I take a look at this again? I'll be there in a second. Okay, Beto.
No, I don't think so. Or do we do the class to get the C-squared? Yeah, we do, right?
No.
Where's that? Kaylin.
What? How do you do it? No, I just learned how to simplify to 0.
Me? I'm so good.
I do, but I don't know like how to get it. What do you do after you do that?
Monia, so are you doing number 2? Are you doing number 2?
Okay, look, when you find the derivative of that, how would you simplify this? Or what do you do after? Do you know what I'm asking?
Ouch.
Okay, to find the derivative, you use quotient rule, right? Okay, so you get that, right? After you do that, you're supposed to equal it to 0 to get the candidates, right? Okay, would you have to simplify this, or I mean, how would you find the candidates like that?
You're saying the same.
They said
Yes, what?
Delia, simplifying.
I told you.
But then what do we do? Why you can't do anything?
But it can't be like that because this is already squared.
Yeah. And then the great thing is that they try to
Let's do BB.
Okay. I'm coming at you.
multiply the top out. Like you know how Spider-Man does it? You know,
Spider-Man
He
just
said
got
I
Spider-Man.
mean, I ain't like you know, like when you multiply each one out, and then you get like a.
Okay, hold on, hold on, hold on.
After, like, we're trying to find the derivative.
Okay, so you found the derivative and the derivative looks good, and you're setting this whole thing equal to 0.
Because you want to get the candidates.
Indeed, you want to find the candidates.
So our question is, how would we find the candidates, or do we have to simplify this first?
It might be a good idea to simplify first.
Okay, and then how would you simplify it? Because
Okay, so let me catch up to you. Alright, so I was just talking to Delia, but I know that this happened last period as well. Okay. So a little low d high minus high d low. Low, little quotient rule, and everybody's okay with the quotient rule. Okay, but the thing is, the reason that you found the quotient, you found the derivative, is you're trying to figure out where g prime of t is equal to 0, or g prime of t doesn't exist.
Yes.
Right, these are like, this is the skill from last unit that I need to make sure everybody can do. Everybody needs to be able to find a derivative. Now the tough part is, how do you solve that? So apparently what the Spider-Man groupies over here want to do is they want to multiply out the top. That's okay. If you multiply out the top, what happens? We get 2t cubed minus 8t minus 2t cubed. In the bottom, t squared minus 4, the whole thing squared.
wait. Oh
The 2t cubed and that 2t cubed cancel out, and this is my derivative. So the question is, when does g prime of t equal 0? What has to happen? Your derivative is a fraction. What would have to be true for the derivative to be equal to 0? The top, the bottom, a fraction. What has to be true for a fraction to be equal to 0?
The same denominator.
For a fraction to be equal to 0, the top has to be equal to 0. You need 0 divided by a number in order to get 0 as an answer. So what's the value of t?
0.
T equals 0. Okay, but we also have to look for, like, cusp points. G prime of t does not exist. What would have to be true there? Why would the derivative not exist? Not 0 over 0, but 0 in the denominator. Okay, so what would have to happen for t squared minus 4, the whole thing squared, to be equal to 0? T equals 2 is one of the places. If you're not sure t squared minus 4, the whole thing squared is equal to 0, that means that t squared minus 4 has to be 0. So t squared is equal to 4. And I heard t is equal to 2. Or negative 2. Okay.
Wait, what is that?
What is that?
Is where it is not equal to 0. I mean, it's not exist.
If the denominator of the fraction is equal to 0, then the whole derivative doesn't exist. These are the places that cause the denominator to be equal to 0. Okay, so how many endpoints? Whoa, endpoints. 2. How many internal candidates?
1, 3.
Got one. Just the one.
He's 1.
Okay, all right, good. We're getting some attitude now. You're like, wait, there's 3, 1, 0, 2, 14. I don't know anymore, and I don't care. Okay, the interval is what determines everything. What's your interval? -1 to 1. How many internal candidates are there?
1.
1. This is the only internal candidate. The other ones, although they do make the derivative equal to 0, these are outside the interval. And we don't care because we don't get to see that function. We don't see that part of the function. So your last piece, and this should be the easy part, just evaluate. You evaluate at your candidate. You evaluate at each endpoint. You're going to plug them in. You're going to come up with your conclusion. Done. That's an interesting noise.
Wait, what?
So absolute max.
It's 0, 0. There's two. If they both have the same y, can
That's
it be
possible.
2 of them?
Absolutely.
Absolute wrong.
No. Not if you do it correctly.
What did he say about it?
He said yeah.
So g of -1 is -1 squared.
Yeah.
Okay. So if all goes well and you plug in everything correctly, g of 0 is equal to 0, g of -1 is -1/3, g of +1 is -1/3. And our conclusion, where's the absolute max?
0, 0.
Absolute max, 0, 0. Okay, absolute min?
-1, -1/3, and 1, -1.
At -1, -1/3, and
Yeah.
at 1, -1/3. They both count as absolute minimum. And all the friends are okay? Okay. Kevin, you're good? So now you guys have basically tricked me into doing 2 of the 4 homework problems for the weekend. Hold on, I'm not going to be tricked further.
Can you try number 4?
Yeah, no, Jose. I was so excited, I was ready to jump. No! Okay, here, so your homework assignment will be different from second period. Okay. Second period, I only did 1 of the 4. What I want you guys to do is redo last night's homework assignment.
Okay.
Redo last night's homework assignment. Yeah, I see you, son. So you're, okay, hold on. Some of you are like, but I'm already done. No. Let's go back and fix it. Do it the right way. I am picking this up on Monday. Give me that, cheater.
Okay,
still don't understand that.
Miss
Well, that's not my fault. Yeah.
Birdie, we don't have to finish this homework? Or we do?
I want you all to focus on redoing assignment 54. Don't worry about going any further with assignment 55. Assignment 54, the one that some of you pretended to take out earlier.
Can we do number 4 then?
Can we do the 10?
Not right now because I want to move you guys around a little bit.
That's actually the class.
All right, so here's what I need you to do, please. I need you to find somebody new to work with. We are going back in the unit guide for the next 22 minutes. You're working with somebody different. You have 4 minutes with your new friend. Don't worry, this isn't permanent, it's just a temporary breakup. On page 23 in the unit guide, there are 6 questions here. I'm curious to see what you and your newfound friend can do in the next 6 minutes. 4 minutes. 4 minutes. Page number 23. Page 23, 6 questions, see what you can do.
Oh, 6 questions.
What's the difference between a relative max and an absolute maximum?
Oh. Of all the bad ideas I've seen today, this could be the worst. And after all that, there was that brilliant acting yesterday.
No, wait. Oh, yeah.
This is wording.
Do all continuous loops have no. Like the linear function?
I guess that's an explain. No,
What do you mean?
that does have an absolute maximum.
Oh, yeah. So what would be an example?
Circle.
That one, no.
That's not a function.
No, not a
I'm just
function.
testing them.
Okay, so
Excellent.
so the linear function.
It's like this one. The linear has absolute maximum.
Right, 'cause I think what you guys are getting stuck on is you're thinking about like if it's a horizontal line. In the horizontal line case, what is your absolute max? Every point is your absolute max because they all have the same y value. And they're also all the absolute minimum.
Wait, but this one does have an absolute maximum.
Oh wait, so
Because this is going to
putting
continue to negative
putting
and
attention.
Global is
No absolute max.
global is red.
What did you say?
Isn't global?
Oh,
Yeah.
I keep
or
thinking this is at the highest point, right?
Yep. Really?
When it changes from decreasing to increasing,
Unconsiderable
the
weight
net
of
prime goes from negative to
There ain't
positive.
none, son.
Yes.
What if the closed interval is 0 to infinity?
That's not a closing
Wait, that's not
interval.
That is the closed interval.
No, because infinity is a welcome.
No way.
Okay.
I don't know. Because we had a question with the interval.
A closing interval is a bracket. If we would have put infinity as the open bracket.
1 minute. Yep.
So, okay, what they're arguing is
We're
that
arguing, I let him ask it.
infinity is parentheses, right? So,
Correct.
okay.
So it is not a closed interval.
She called you over here.
No, I just wanted to make sure. Oh, sorry. Why is it true? Why is it true?
Because you're looking at like a certain position of the graph. And they do. Like you're not looking anywhere beyond that.
Oh, well, because it's closed, right? So that's what it is.
Yeah, so you're always going to find something higher.
Alrighty, friends, here we go. What's the difference between a relative max and an absolute max? Easy.
Highest point and increasing to the.
An absolute max is the highest point on the graph.
You're right.
The relative max
Increasing.
changed from increasing to decreasing. Different definitions. Sometimes is a relative max an absolute max? Can a relative max be an absolute max? We've seen that, like an upside down parabola, that would count. Alright, number 2, what's the difference between a global minimum and an absolute minimum?
There's no difference.
Same thing. Same thing. Absolute minimum is the one that I tend to use, but some textbooks call it a global minimum. The other vocab word we had yesterday, we talked about relative min, and there was a different adjective. Local. Relative min, local min mean the same thing. Okay, number 3, do all continuous functions have an absolute maximum and an absolute minimum?
No.
Wait, one more time.
No.
Do all continuous functions have an absolute max and an absolute min?
Oh no.
No.
Yes? No?
No.
No? If the answer is no, I need a counterexample. I need one continuous function that doesn't have an absolute max. Ashley?
Can I just draw it?
Uh-huh. I saw you draw that. Is this a continuous function?
Yes.
And it has no absolute maximum why?
Because there's no end point. Wait,
Wait,
there's no highest point.
There's no highest point. The graph continues going on forever and ever and ever.
Yes.
Okay, On a closed interval, will all functions have an absolute max and an absolute min?
Yeah.
You have a closed interval.
Yes.
All functions have an absolute max and an absolute min?
Yes.
Nobody wants to say no to this one.
Except for the flat line.
On a closed interval, question number 4. On a closed interval, will all functions have an absolute max and an absolute min? And the answer is no. I need an example of a function on a closed interval that doesn't have an absolute max or an absolute min.
Y equals
No,
2.
they're
You got one?
all absolute max.
Whenever it's like the line is like constant.
Okay, you're actually going in the other direction, and some other folks said that as well. Like, what if it was just a horizontal line like that? Is there an absolute max?
Yes.
Yes, every single point counts as the absolute max. Is there an absolute min?
Yes.
Absolutely. I don't want to think about this. I want a function on a closed interval where there is no absolute max or absolute min. And here's what we're missing. What if we look at this function on that interval? Is there an absolute max and an absolute min?
No. Oh. Isn't that 1 over
Because you
x?
don't have a continuous function. This is the graph of 1 over x. There, we have a closed interval, but we have no absolute max and we have no absolute min. All right, number 5. Can a function have a relative max, which is not the global max? A relative max that's not the global max. Relative max that's not a global max.
Wait, what do you mean?
Yes. Yeah.
Yes.
What would that look like, one?
I don't know. A random. Oh, the one from the homework.
A relative max that isn't the absolute max. You guys sketched a lot of these yesterday.
The one that you drew for the
For
homework.
the first one.
The one you drew for the goof.
Oh yeah, I've heard that. The one I drew from earlier. I think what we mean is
Yeah, that.
that one.
Yeah.
Relative max. Relative max. This guy's the absolute max. This one's not the absolute max. Okay, last one. As completely as possible, state the extreme value theorem.
On every function.
There are 2 conditions to use the extreme value theorem, and you want to get some of these written down, otherwise I don't know what you're doing here. Extreme value theorem, there are 2 conditions. The function has to be continuous,
That's infinite.
and not differentiable. The function has to be continuous is the first condition. On a closed interval. If you have a continuous function on a closed interval, those are the 2 conditions. What are you promised?
That there will be a relative extrema.
Nothing about relative extrema.
Absolute max and absolute min.
If you have a continuous function on a closed interval, you have to have an absolute max, you have to have an absolute minimum. This is what we're guaranteed.
Yeah.
And all the friends are mostly okay?
Yeah.
Alright, now I really want to push you, so why don't you guys go back to where you normally sit.
No, I want to
Say goodbye to your little friends. It was fun while it lasted. We're going to spend the last 15 minutes or so today pushing your thinking further. And we're going to continue with this on Monday and Tuesday. We're going to look at a lot of application questions.
It's easy, it's not that hard. You just gotta do your algebra.
As future mathematicians, we're going to classify these problems as optimization problems. Optimization problems are questions where you are being asked to find the best solution. The greatest amount, the least amount, the smallest amount, the biggest amount. These are optimization questions. So here comes your first one. A sheet of cardboard 2 feet by 2 feet will be made into a box by cutting equal sized squares from each corner and folding up the 4 edges. What will be the dimensions of the box with the greatest volume? So think about this situation for a second. Talk to the folks around you. What's going on in this problem? What's being built? How is it being built? What's going on?
A sheet of cardboard 2 feet by 2 feet made into a box by cutting equal size squares from each corner and folding up the door. What is the Oh, I hated this question. This came out of geometry.
Optimization problems have a lot of geometry going on. You start off with a piece of cardboard. And what happens next? You fold it, but the thing is you can't fold a piece of cardboard. You can't just take a piece of cardboard or take a piece of paper and fold it, and fold it in the front and fold it in the back. You can't do that even if you try, because what's going to happen, right, if you fold up the sides, you fold up these sides, you can't fold up the front because of this piece over here. So what you have to do to actually take a piece of cardboard and turn it into a box is you cut out the corners.
Let me just restrict it.
Are we okay? All right, so let's draw what the new box looks like. Okay, hold on a second. So here's my new box showing off my mad geometry skills. There's my new box. What I want to do is I want to maximize the volume. Well, I know, and all of you guys know how to find the volume of a box. We've been doing this forever. Volume of a box from geometry? Length times width times height. We know that. Okay. If I think about the cardboard that I started with, and I think about the box that I'm building, what's the length now? Here's my length. Here's the width. Here's the height. How long is the new box? It started off being 2 feet long. And what we did is we cut out a little square from this corner, and we cut out a little square from that corner. And so what that means, and I just heard it up front, is that the length is now 2 minus 2x. Because you threw out this little box that had a length of x, you threw out this little box that had a length of x, and your new box has a length of 2 minus 2x. What about the width? The width started off 2 feet long. I threw out this little square. I threw out that little square. What's the new width? 2 minus 2x. Think about this one before you answer. What's the height of the box? X. Think about how you make this box. You cut out the little corners, you fold up the sides, and the height of the box is going to be determined by how big is the square that you throw out, because you're just going to fold it up at you. And so the height is going to be X. So now that I've got that, my volume is going to be 2 minus 2x times 2 minus 2x times x. Good news. You've taken your geometry problem and you went and you found the equation that we're going to use, the equation that I want to try to make as big as possible, or as small as, in this case, as big as possible. And I bet your calculus skills kick in right away. How do we optimize? How are we going to find the biggest volume? How are we going to find the biggest volume, the biggest value for this function? What have we been doing for the last 2 days? When I say biggest, I want you to be thinking about it's an absolute max kind of question. And the way that you guys find the absolute max all of the time, you're going to find the derivative, you're going to set that derivative equal to 0, you're going to find your candidates. Go ahead, go find the derivative. Go find the candidate or the candidates. Yeah. Nice.
No, we can't.
Yes. So it looks like you're doing a little bit of algebra before you do the calculus. That's fine. Just do it right.
Plus first.
Some people seem to be a really big fan of the extended product rule.
So we don't have a close enough.
there seem to be three things happening right now. Some people are using the extended product rule because we have three things being multiplied together. Some folks are doing a little bit of algebra first and then taking a derivative. And then other folks have completely forgotten everything I've taught you about finding derivatives. It's the third group that makes me saddest of all. My advice would be do the algebra first. So maybe you want to go off on the side here and say 2 minus 2x times 2 minus 2x. 2 times 2 is 4. What do we get? Negative 4x. Negative 4x. 4x squared. So 4 minus 8x plus 4x squared is what I get if I multiply these two together. Multiply it by x. 4x minus 8x squared plus 4x cubed. Just a little bit of algebra. If you do the algebra first, I hope the calculus is super easy. All right, derivative of 4x minus 8x squared plus 4x cubed, what do we got? We've got 4 minus derivative of 8x squared, 16x plus derivative of 4x cubed, 12x squared. We found the derivative. Why did we find the derivative? We want to set this equal to 0 and we want to solve for your candidates. All I need to do is a little bit of algebra now to solve that equation. Now if I'm really in my algebra mode, I'm probably going to rewrite this in standard form, so it's in descending powers. 12x squared minus 16x plus 4. Options, maybe you want to quadratic formula.
Nah.
Maybe you want to try to factor with the mama diamond, to write the box in the diamond. But those are some big numbers. Juan, what did you say? Can we take out a 4? If you see that you can factor out the 4, I bet it's more likely now that you're going to be able to actually factor this. 3x squared minus 4x plus 1, you guys should be able to factor that. And just for the sake of time, it's 3x minus 1 times x minus 1. That should not be the hard part for anybody in the room. So where are the candidates? X equals 1/3, or x equals 1. These are the candidates. Now, Kaylin mentioned something earlier, or it was Ashley that mentioned it earlier. We know the candidates, but there's something that we're missing. We actually don't know the interval. We don't know the endpoints. The endpoints, you're going to have to think about the actual situation here. In all the other problems, I've told you the endpoints. Think about the geometry of this problem. If x is how large the square is that I'm removing, what's the smallest x value I could use? X is the length of the square that I take out. What's the smallest that length could be?
1.
I would argue 0 is the smallest value that you can take out. Basically what you're saying is don't cut anything.
Yeah.
Okay? Is there a biggest value to consider?
2. No.
2? Last class was convinced of 2 as well, and I know where the 2's coming from. Think about the geometry of this situation. 2's not possible. 2's not possible for a completely different reason. How long's the cardboard?
2.
2 feet. How many squares are we cutting out?
4.
Okay, but on a side?
1.
2.
You want to take the whole piece off?
What's the farthest I can come in? 1. The largest square I could cut would be a square that is 1 foot on a side. So those are your endpoints. Okay, stay with me real quick. You got we did the hard part.
Okay.
We got the candidate. I know it's a little cold. We've got the endpoints. It's time to evaluate. I want to look at the volume at 0, the volume at 1, and the volume at 1/3. 0 and 1 because those are the endpoints. 1/3 because that's the candidate. What's the volume if I take out a square of side length 0? If I go back to my original function. 0. Does that just make sense?
Yeah.
Right? What we're saying here is I didn't actually cut out squares. I didn't actually do the thing I need to do to make a box. I'm going to get 0. Well, what if I go to the other extreme? 2 minus 2 times 2 minus 2 times 1 is 0. I went so far. I cut a foot this way. I cut a foot this way. I threw away the squares, and I left myself no cardboard. The last one, 2 minus 2 times 1/3, 2 minus 2 times 1/3, times 1/3, I'll tell you just for the sake of time, is going to be 16/27. Basically, your candidate, in this case, has to be the absolute max. Are we okay?
Yes.
So to finish it off, just make sure you go back and read the question. What are the dimensions? When I ask about the dimensions, what I'm asking for is what's the length, what's the width, and what's the height. The length is going to be 2 minus 2 times my 1/3, which is going to be 4/3. The width is 2 minus 2 times 1/3, 4/3. The height is 1/3 feet, feet, feet. Nice job on the first application problem for optimization. This is what Monday, Tuesday, and Wednesday are going to look like and feel like. We're going to be okay. Don't be absent.